right, my friends. Section 9.3 is called Hyperbolas. We're on part 2 now. We'll be talking about the derivation. So hopefully the elliptical derivation made sense, because this one is very similar. So I have posted some, paper for you if you can, print it out if you can't, and I guess hobble along to your best. If you don't have a printer, I fully understand. I've lived most of my life without a printer. Anyway, so this picture here looks like it could be, I don't know, a fish or a rocket, I don't know. Anyway, it's really nothing quite that exciting. We're going to use it to really understand what the definition of an ellipse was, and then we'll also use it to hopefully really understand what the definition of a hyperbola is. So first let's play with the ellipse here just a second. And these 2 points here will serve as foci. So let's say I pick a point here, that's on, and I purposely picked one of those points where the concentric circles intersected there. So let's say I pick that point and I try to figure out how far that point is from one of the foci. And that's where the concentric circles are helpful. So I could just count how many rings, I get, that it takes me to get from the focus to that point. So 1, 2, 3, 4, 5, 6. So I'd say for distance 1, there is 6. And then if I was to do the same thing with that point and the other focus, and just counting the distance, so like 11. Okay, so I have 6 and 11. If I was to pick any other point on that ellipse, say there, and ask you, how far is it from this focus, that would be easy to count. 2, 3. Based on what we've already talked about with ellipses, what would you guess that distance 2 would be? Like this distance right here. Could you figure it out without counting it out? Here, I'll count it out. 1, 2, 3. Oh goodness, it's hard. 9, 10, 11, 12, 13, 14. 14. I think. Okay. And was 14 what you would have guessed? And let's say I pick this point, let's say right here. That's on the ellipse. Here, this little distance is obviously 1. What would you guess the other distance to be? And I would guess 16. And how come? Remember that an ellipse was the collection of all points such that the sum of the distance between any point on the ellipse and 2 fixed points called foci was always the same constant value. 6 and 11 made 17, 3 and 14 also made 17, and 1 and 16 always made 17. So really what I'm just trying to do here right now is drill in what we knew about an ellipse, that it was the collection of all points such that the sum of the distances between any point and 2 fixed points called foci was always the same constant value. So I'm going to take this stuff off, and now we're going to try to ignore this ellipse. It's kind of served its purpose for now. Now we're going to focus on this piece, which I'd like to show will be half of a hyperbola. I'm going to take these distances off. So we'll talk about new stuff here. Okay, so let's say I pick this point right here. It's on the hyperbola, just happens to also be on the ellipse. If I was to figure out, how far it is from this focus 1, 2, 3, 4. Looks like it's 4 units. Okay. And then if I was to figure out how far it is from this focus, 1, 2, 3, 4, 5, 11, 8, 9, 10, 11, 12, 13. Okay. Let's say I pick another point that's on the hyperbola. This point right here. And I count how far is it from this focus. 7. Okay. Anybody have a guess without counting what the other distance is going to be? This distance from the point that's on the hyperbola to the other focus. Okay. Got your guess? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Was that your guess? Okay, let's see. Let's do another one. Let's do this one right here. So distance 1 would be 1, 2, 3. Okay, guess. What do you think the other distance is going to be? The distance from this point to the other focus. Got it? Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Was it 12? Was that your guess? Okay. So what's the relationship this time between the two distances? The distance from a point that's on the hyperbola to one focus and the distance from that same point to the other focus. What's that relationship every time? 13 minus 4, 9. 16 minus 7, 9. 12 minus 3, 9. So what we're getting at here is the definition of a hyperbola on an xy plane. Instead of the sum of the distances always being the same constant value, it's going to be the difference of the distances is always the same constant value. So here we go. Definition. A hyperbola is the collection of all points in a plane such that the difference between the distances between, let's word that a little differently so it doesn't have two betweens. The difference of the distances between any point on the ellipse and two fixed points called, you guessed it, foci, is always the same constant value. Here we go. Let's see. Now for a comment on what that constant value would be. I think I'd like to bring back an example that we've done before for that. So if you look at part B here, let's say here's a point that's on your hyperbola, okay? So let's think about how, what's the difference in distances between this point and this focus and this point and this focus. And if you think about subtracting those two values, I hope you can see that this little distance between the outer edge of your boundary box and the focus would kind of cancel this distance out. So basically, the difference of the distances is just going to be the length of this little piece of the transverse axis that's between your foci here, or not your foci, sorry, wrong word, your vertices here. So in this case, that would be 6. But in general, if that wasn't a 9, if that was just like an a squared, and if this wasn't a 16, if it was just like a b squared, then the difference of the distances would end up being that distance in between here, which would just be 2a, which is great because that's what it was with ellipses too. So that same constant value is 2a there. So what is that going to do for us? It's going to help us get started with our derivation. So the derivation is going to start out, with the distance formula. So, d1 minus d2 has to equal 2a there. Okay. And then remember from the first video, we mentioned the Pythagorean identity. For hyperbolas. And it is refreshingly similar to the Pythagorean identity that we know and love from geometry. So keep this in mind because you'll need it as we go through the derivation. Now for this picture here, I'm going to bring this back for a second, and I'm going to clutter it up just a little bit. The first thing that I'm going to do is draw the other half of the hyperbola. So you could do that pretty easily just by getting, you can see this vertex here is 3 points in from the focus. And then we could get these little guys pretty easily where the ellipse and the hyperbola intersected. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. There we go. And then just kind of do your best from there. Okay. So there's the other half of the hyperbola, and then I'm also going to draw an XY plane in. So I'm going to make this hyperbola be centered at 0, 0 simply by putting the x-axis here. And then by putting the y-axis in, let's see, let's count our distance. 1, 2, 3, 4, 5, 6, 7. Oh, did I miss? I did. Good night. 2, 3. There we go. Okay, 1, 2, 3, 4. Okay, so then I'm going to put the y-axis just down the middle here. Okay, so your hyperbola is just this piece right here. And then if I was to draw that boundary box that we've mentioned before, it would be kind of interesting to do it. I would have to kind of grow it in a way from like where the asymptotes would go, which is kind of hard. But let's say I think one asymptote, oh, there's no way it's there because that does not even go through the origin. Boo. I'm going to trust the pre-printed hyperbola a little more than the one I drew. Okay, let's say I drew the asymptotes. I'm just kind of trying to make it so that I get the asymptote kind of like lines up with the outer edges of this piece. And then what I could do is I'd know that the boundary box would go out this far here, and I could just go up, boop, 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 until it hits the asymptote. It's kind of fun. There we go. Okay. I'm going to really kind of darken this boundary box here because this picture is getting super cluttered. Okay. So here's what this little boundary box helps me to know. So this distance would be A right there. And then this distance would be B. And then the distance from the center to the focus would be C. B, A. There we go. Okay. So with that said, then if we were to pick any point on your hyperbola, call it XY, like that, then what's so special? What's that perfect relationship between X and Y that makes a point be on the hyperbola as opposed to not? Well, it is simply that the distance between XY and one of your foci, and the distance between XY and your other focus is always the same constant value. So what are the coordinates of this focus right here? They are C0. What are the coordinates of this focus right here? They are negative C0. So step 1 in your derivation is simply that distance 1 minus distance 2 has to always equal 2a. Well, what would distance 1 be? It would just be maybe, let's do the longer distance, I guess. It would be distance formula applied between xy and negative C0. So square root of quantity y minus 0 squared plus x plus c squared. Second expression, y minus 0 squared plus x minus c squared. And the difference between the two distances is always going to be 2a. All right, the rest, honestly, is just a bunch of algebra to clean this up. And the end goal is to show that it's going to be this cute, x squared over a squared plus y squared over b squared equals 1. That's the goal. So to do so, remember, if you square both sides now, this is going to get worse than you want it to do. So let's simplify this root right here. I think I'll delay squaring x plus c squared out. Let's subtract this root over, so let's say 2a minus square root of that root. Now let's square both sides. On the left side, it does get rid of the root like you'd like. On the right side, you'd have to use the FOIL process to figure out what you'd have. Like so. Look for things to vanish. The y squareds would vanish for sure. We could expand the binomials here. like that. Look for more things to vanish. Combine like terms. And what would we now have? On the left side, we'd have 4xc or 4cx. On the right side, we'd have 4a squared minus 4a times the square root of y squared plus the quantity x minus c squared. From there, I personally would divide both sides by 4 or multiply both sides by 1/4. I would also subtract the a squared over. And then at this point, if you square both sides, we should be able to say bye-bye to all square roots. Okay, I'm going to finally make this thing alphabetical. It's been bothering me this whole time. Okay. There we go. Okay. Now on, let's see, what could we do now? All right, let's expand the right side out. X minus c squared is x squared minus 2cx plus c squared. Let's distribute the a squared in. There we go. All right, my friends, let's hope that some things vanish sooner rather than later. Do we see anything that could vanish? All right, I do. Okay, do we see anything else? Nope. Okay, so we've kind of done what we can from here. Now at this point, notice that there's a whole bunch of c squared stuff in our work, and we really don't want there to be any c squared stuff in our work. We want this to look this cute, and there's no c involved in the whole thing. So this would definitely be a moment to use the Pythagorean identity for ellipses. So just a quick there we go. Okay, so let's replace all the c squareds with a squared plus b squareds. Just be here and here. So we'd have a squared plus b squared times x squared plus a to the 4th. There we go. Distributing what's left, we'd have a squared x squared plus b squared x squared plus a to the 4th equals a squared y squared plus a squared x squared plus a to the 4th plus a squared b squared. All right, my friends. The a to the 4ths vanish. Anything else? A squared x squared. Bye-bye. Okay. And let's look at what we have left. We have b squared x squared on the left side. I'm going to subtract a squared y squared over. but I'm going to leave the a squared b squared on its own side. Dividing both sides by a squared b squared. Well, on the right side, it would give you the loneliest number. And then on the left side, when you distribute this in, I'll just show this in 2 steps, I guess. And then look for things to cancel. And then what did we do? We just finished it. It is that adorable. Notice that the x squared term is positive. That is because we were working from something that opened horizontally here. And so there you go. And so what have we done by deriving it? We've really hopefully satisfied any curiosity you may have had or any questions you may have had about how things end up being the way they end up being. There we go. We'll do a couple more examples on part 3, and then you'll be done.